Hello, and welcome to a journey of discovery where science and curiosity intersect. Today, we'll turn our gaze toward a world that's been called Earth's twin sister, a planet shrouded in the mysterious veil of perpetual clouds. That is Venus, named after the Roman goddess of love and beauty, yet concealing a nature completely opposite to that graceful name. In the most fundamental measurements, Venus is truly an almost carbon copy of our home. It's only about 5% smaller than Earth, and its surface gravity reaches 90% of the gravity you're feeling right now. Like Earth, this planet formed 4.5 billion years ago from the same type of cosmic material that condensed into our world. Yet, beyond those structural similarities, Venus is more of an opposite than a twin sister to Earth. It's an eccentric world that rotates in reverse, where the sun rises in the west and sets in the east. Here, a day is longer than a year, if calculated the Earth way, and there's absolutely no change of seasons. And if you move in a little closer, the truth becomes cold and horrific. Venus, our closest planetary neighbor, is a genuine hell. The second planet from the Sun maintains an average surface temperature of 464 degrees Celsius. Imagine that. That's hot enough to melt both lead and zinc metal. The air there would instantly incinerate our fragile biological bodies. If you stood on the surface of Venus and looked up at the sky, an overly dense atmosphere would reduce the sun to merely a dim, blurred streak of light, and the stars would be completely absent from the night sky. The atmospheric pressure at the Venusian surface is 92 times higher than Earth's. This figure is equivalent to the pressure you would endure at the bottom of the ocean at a depth of almost 1,000 meters, a pressure that could crush a nuclear submarine. It is an arid wasteland with bone-dry air and thick sulfuric acid clouds containing toxins that could destroy all life. But Venus wasn't always a barren land of fire, ash, and dust. According to NASA models and data, the planet may once have been a habitable world, with vast oceans similar to Earth's. However, that was at least 1 billion years ago. No one knows exactly what happened to this world that may have once been so beautiful. The unpleasant one-way nature of time has locked that secret away. But with clues, with the fragments that remain, we can attempt to piece together a picture of this cataclysmic transformation. Venus has been a great mystery for hundreds of years. Author Stephen Guilleau once described it as a warm jungle world, a swamp filled with lizards and monsters. The truth about our neighbor's hellish nature was only revealed when NASA's Mariner 2 probe reported the terrifying temperatures and pressures in 1962. Next came the Soviet Union's Great Venera program. Out of 15 successful missions, 10 spacecraft landed, and 4 of those carried cameras. That is why we have a mere 6 surface images of Venus ever taken to this day. All 4 color images are stained yellow by the thick haze and only show a desolate, cracked rock foundation. Sadly, all those landers quickly succumbed to the extreme conditions. The record belongs to Venera 13, which survived for 127 minutes under the temperature of a pizza oven and the pressure equivalent to 950 meters of water. That was the story of more than 40 years ago. NASA now possesses the world's largest Venus environment simulation chamber, and they believe that current generations of cutting-edge spacecraft could operate on Venus for weeks, even months. But that's a story for the future. Venus missions so far, including the Soviet Venera program and NASA's Pioneer and Magellan, have told us a great deal about this close yet mysterious world. It turns out that Venus is both confoundingly similar and different from our world. Like Earth, Venus has countless volcanoes. Radar images of the surface have revealed thousands of scattered volcanoes. Prominent among them are the pancake-shaped volcanoes, about 25 kilometers across and 2 kilometers high, which erupted a type of highly viscous, honey-like lava that spread evenly in all directions. Additionally, there is a type of supergiant, crown-shaped volcano called a corona. They can be hundreds, even thousands of kilometers wide. Coronae are formed when magma, unable to penetrate the crust, pushes it up into a dome shape. Then, the central part collapses, and lava leaks out the sides, creating the enormous crown-like structure. The largest crown, Artemis, is up to 2,600 kilometers wide, a distance equivalent to the journey from Hanoi to the center of Mongolia. A truly astonishing size. The key geological difference between this twin sister lies here. Volcanoes on Earth are concentrated along the boundaries between tectonic plates. Meanwhile, volcanoes on Venus are scattered haphazardly, seemingly following no rules. Geologists hypothesize that geological activity on Venus occurs at a lower level. It is enough for lava to erupt at some points and pool at others, but it is not strong enough to tear the crust into floating plates as on Earth. In other words, the Venusian crust is very likely a single intact plate. The problem arises from here. If Venus has no plate tectonics, meaning its crust is not continuously recycled by sinking into the mantle and being melted, and if its age is the same as Earth's, then one should rightly find countless ancient impact craters and mouths 3 or 4 billion years old on it. The reality is not so. As of 2017, about over 900 impact craters have been counted on the Venusian surface. Amazingly, all are of a relatively young age, ranging from 300 million to 1 billion years. This suggests that the age of the planet's crust, what we are currently seeing, also lies somewhere within this time frame. Venus formed at the same time as Earth, 4.5 billion years ago. So, where has its original crust, the geological evidence from 3 to 4 billion years ago, vanished to? This paradox raises a chilling hypothesis. Some catastrophic event in the past reset and reshaped the entire planet's surface. The question is, what the hell happened? Of course, no one has the absolute answer, but there are countless hypotheses. One terrifying possibility is this. As heat from the planet's core sought to escape into the mantle, Venus's intact, uncracked crust inadvertently became a giant sealed lid, preventing most of the heat from escaping. Energy accumulated beneath the crust for millions, billions of years, until it exceeded the tolerance limit. Then this lid suddenly burst open in a phase of globally violent volcanic activity. This large-scale eruption created an ocean of magma, almost completely destroying the previous billion-year-old crust. This event not only wiped out the primordial surface, establishing a completely new appearance, but it also destroyed all geological evidence of Venus's distant past. Therefore, the only place where humans can still look and discern a little of Venus's past is its thick, toxic golden atmosphere. Venus's atmosphere contains a colossal amount, 96.5% carbon dioxide. The atmosphere being entirely CO2 is precisely why Venus is hotter than Mercury, even though it is further from the Sun. If Venus had no atmosphere, its surface temperature would only be about 55 degrees Celsius. But CO2 gas has pumped it up to 464 degrees Celsius. Atmospheric pressure at the surface, being 92 times Earth's, means there is a lot of CO2 in the Venusian atmosphere. In fact, the Venusian atmosphere contains up to 480 quadrillion tons of CO2. Meanwhile, the entire Earth's atmosphere only weighs about 5.2 quadrillion tons, and only about 3 trillion tons of that is CO2. An astonishing difference. Naturally, that terrifying amount of CO2 was erupted from volcanoes. Earth's volcanoes also emit CO2. However, unlike Venus, CO2 on Earth is removed from the air by marine algae and plants through photosynthesis. It is then fossilized into oil and coal deposits, and finally sinks back into the mantle during plate tectonics. Without these carbon recycling processes, the present of Venus would certainly be our horrific future. Now let's look back at the Venusian atmosphere. In addition to a lot of CO2, it also has 3% nitrogen. That sounds very little compared to the 78% of Earth's atmosphere. However, don't forget that the Venusian atmosphere is a giant compressed gas cylinder. If you decompress all that numerically small percentage of nitrogen, you would obtain an amount nearly equivalent to the entire amount of nitrogen currently in Earth's atmosphere. At this point, a frightening truth gradually emerges. It seems that Venus began its path with similar components to Earth's. Yet somehow, its outcome was not at all beautiful. And there is still a paradox. Venus's intact crust may have caused energy to pool and triggered a volcanic blockbuster event. However, if Venus's crust has been intact for billions of years, that means the geological activity beneath it should be much milder than on Earth. That is, even if the supervolcanic event occurred, it should have produced less CO2 than Earth, shouldn't it? Yet somehow, Venus still accumulated up to 92 atmospheres of CO2 throughout its lifespan. To resolve this paradox, Dr. Michael Way and colleagues at the Lunar and Planetary Institute suggest that Venus once underwent a period of strong geological activity with tectonic plates floating on the mantle, somewhere between 4.5 to 3.5 billion years ago, before it switched to the mode of a planet with a single crustal plate. But remember, this is only a hypothesis to resolve the carbon paradox. Returning to the Venusian atmosphere. Measurements from the Venera, Vega, and especially the Pioneer probes revealed a key clue about the planet's watery past. They discovered that the concentration of deuterium, a heavy isotope of hydrogen, or hydrogen-2, in the Venusian atmosphere is 120 times higher than on Earth. Deuterium is found in anything containing hydrogen, including water. At normal concentrations, our water contains about 150 deuterium atoms per million water molecules. Deuterium can be created when ultraviolet rays from the sun bombard water molecules in the atmosphere, causing lighter hydrogen H to escape into space more easily. Meanwhile, the heavier deuterium is retained. This massive deuterium surplus is clear evidence. Venus once had vast oceans before the brutal greenhouse effect boiled them all away. Scientists are unsure about the exact amount of water Venus once possessed. It could range from just 3% to 100% of the water volume of Earth's modern oceans. What is certain is that they evaporated completely, perhaps before the resurfacing event occurred. This is proven by the apparent lack of any trace of rivers, lakes, or oceans remaining on the current surface of Venus. The disappearance of these oceans may have accelerated the disappearance of plate tectonic activity on Venus, giving way to a single crustal plate. Because water plays a role in reducing the rigidity of tectonic plates, making them more ductile and malleable to sink into the mantle. When the water vanished, the planet's crust became hard and monolithic. However, we don't need to mourn the fate of water on Venus because its disappearance was almost a matter of time. Don't forget that Venus is 30% closer to the Sun than Earth. That means it receives almost double the amount of heat from the Sun's light. However, it is important to note that the Sun's output is not a constant. In fact, the Sun itself is gradually brightening over time. This means that 3 billion years ago, Venus received a much smaller amount of light, only slightly more than 40% of what Earth receives today. Also, don't forget that Venus is completely covered by clouds. This veil helps it have an albedo, reflectivity, of up to 70% of the Sun's light back into space compared to only 30% for Earth. Finally, Venus rotates very slowly. One rotation on its axis takes 243 Earth days, even longer than a Venusian year, only 225 days. You heard right. Venus is the world where you can celebrate your birthday every day, sometimes twice a day. Climate models indicate that when Earth-like planets rotate slower, they tend to be cooler due to cloud accumulation on the side facing the Sun. All these factors, when combined, suggest that Venus once had a temperate, potentially habitable past. A significant study by Michael Way and Anthony Del Genio from the Goddard Institute for Space Studies, published in 2019, suggests that Venus may have once been a temperate planet containing liquid water for 2 to 3 billion years. It wasn't until some brutal climate change event occurred, possibly around 700 million years ago, that the planet's atmosphere became dense and extremely hot, simultaneously scorching about 80% of the planet's surface. However, there is a flaw in this 2019 model. The two researchers assumed that the ancient Venusian atmosphere had only a very small amount of greenhouse gases, like CO2 and methane. That is, they are assuming that the entire 92 atmospheres of CO2 currently on Venus were erupted within the last 1 billion years, mainly after plate tectonics ceased and the crust became the sealed lid. This brings us back to the carbon paradox presented above. A planet with weak geological activity, with a monolithic crust, should not have erupted that much CO2 in a short period. Thus, the possibility of life existing on Venus in the past remains open. However, it would be truly devastating if living organisms once thrived on this sister planet 2 to 3 billion years ago, only to be erased without a trace. After all, what event could transform a temperate, possibly life-filled planet into a hell for even the fiercest monsters? We may never find the answer to that catastrophic event. But could life on Venus, if it truly once existed, have adapted to the extreme change fast enough to possibly survive until today? That is unfortunately the topic of another video. In a way, we have been incredibly lucky to be near a planet like Venus. The universe seems to have given us a gift, an opportunity to study a similar yet suffering version of our home planet. Venus is a natural laboratory. It is an opportunity to recognize what can turn our home into hell and force us never to make that mistake. When we look at Venus, it seems like we are looking at our own future. It's no exaggeration to say that Venus is the endpoint for most Earth-like planets. That is the ultimate, inevitable fate as host stars gradually increase in brightness. In the next billion years, as our Sun gradually increases its output, the heat received by Earth will exceed the equilibrium threshold. At that point, all Earth-like planets will encounter a runaway greenhouse effect. The oceans will evaporate, and water vapor, a powerful greenhouse gas, will soar the temperature even further. And after that? What will happen after the water completely evaporates? Our civilization will not exist to witness it, but right now, Venus has given us the answer. After that is only hell. Now imagine how many Venuses might exist out there in the Milky Way. Billions upon billions of barren, desolate hells. And those are billions upon billions of biospheres, organisms, and civilizations that may have been completely destroyed on their own home planets. It's terrifying just to think about it, but this is the harsh reality of how the universe operates. Venus is not just a planet. It is an urgent warning etched in the sky, an invaluable scientific legacy of irreversible climate collapse. It teaches us that the difference between a verdant paradise and a melting hell is sometimes just a thin line. That line is determined by how a planet handles carbon and water. The mystery of how Venus abandoned its path to becoming a temperate world and how a colossal amount of CO2 accumulated without strong plate tectonic processes remains one of the biggest questions in planetary science. Did it go through a period of ancient plate tectonics? Or did its monolithic crust truly cause a global supervolcanic catastrophe? Whatever the answer, it will determine whether life could have thrived on Venus for billions of years, and more importantly, whether humans can avoid that fate. We will continue to follow future missions like NASA's Veritas and Da Vinci Plus, because only by exploring our twin sister more deeply can we truly understand our own past, present, and future. Right now, you are drifting through a hole in space nearly 2 billion light-years across. That is not a metaphor. Scientists confirmed this fact in 2013, yet most people on Earth remain completely unaware. We are living inside the KBC Void, a cosmic desert, where the density of matter is 20% lower than the universal average. This immense emptiness is warping our very measurements of reality. From this peculiar location, the universe appears to be expanding faster than anywhere else. It is breaking our most fundamental equations. In this journey, we will travel through the discovery that shook cosmology, explore why 90% of space is empty, and finally, reveal what it means to exist on this cosmic periphery. If you're ready to see the universe differently, hit the like and subscribe buttons, and let's begin together. Brace yourself, here we go. In 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, were performing a seemingly simple task: counting galaxies. They mapped the locations of 35,000 galaxies spanning billions of light years. And then they noticed something impossible. The numbers were wrong. Everywhere they looked near Earth, the number of galaxies was less than what it should have been. Not slightly less, but up to 20% less. This pattern extended outward in every direction, forming a colossal empty sphere, reaching up to 2 billion light-years in diameter, and we are situated right near its center. This is not a small gap between galaxy clusters. This is a void on a scale that should not be allowed to exist under standard cosmological models. The researchers triple-checked the data using multiple different galaxy surveys and examined the sky from various angles. The result remained frighteningly consistent. Our galaxy and everything surrounding it is located inside a gigantic, low-density bubble of space that dwarfs every other structure we've observed. The discovery was given a rather mundane name: the KBC Void, an acronym of the 3 discoverers' names. But there is nothing mundane about what it represents. According to the standard cosmological model, the universe should be homogeneous, uniform when we zoom out far enough. Sure, galaxies cluster together and leave empty spaces in between. That's normal. But a region so vast with such a significant deficiency of matter exceeded the limits of what random chance could explain. Computer simulations of the universe's evolution from the Big Bang rarely produce voids this large and empty. When they do occur, it's due to extremely rare initial conditions. Its statistical probability is less than 1 in 1,000. Some scientists calculate that it requires a 10 sigma deviation from the average density. In other words, it is so unlikely that you might not find one like it in the entire observable universe. Yet, we are living right inside one. Immediately, the implications began to spread. If we reside in such an anomalous location, could it be skewing every measurement we take? When we point telescopes at distant supernovae to measure the expansion rate of the universe, are we seeing the true universal expansion rate or just a distorted local version? The void hypothesis offered an answer to one of the biggest mysteries in modern cosmology: the Hubble tension. For years, scientists have measured 2 different expansion rates, depending on whether they look at the early universe or the nearby universe. The figures differ by up to 9%. It sounds small, but it represents a crisis. Both measurements are extremely precise. Both should yield the same answer. But they don't. If Earth is situated inside a colossal underdensity region of matter, the gravitational pull from the dense matter surrounding the void would tug strongly outward on the galaxies inside it. That would add an extra velocity to the movement of galaxies receding from us, making the local expansion appear faster than the average. Suddenly, the contradictory measurements made sense. We weren't measuring the universe incorrectly. We were measuring from inside a hole. This realization changed everything. But it also raised an unsettling question that cosmologists are still grappling with. If our position is this unusual, can we trust anything we think we know about the universe? What follows will reveal just how strange our cosmic neighborhood truly is. Cosmic voids are not entirely empty, and that itself makes them stranger than their name suggests. When astronomers call a region a void, they mean it contains far less matter than the average. But matter still exists there. The void surrounding us has only about 15% of the normal cosmic matter density. Imagine it this way. If a typical region of space had 10 galaxies in a certain volume, that same volume in the KBC Void might only have 1 or 2. The galaxies haven't entirely disappeared. They become lonely islands, scattered in an ocean of nearly nothing. Stretching between these solitary galaxies is space containing mainly dark matter, dark energy, and sparse wisps of hydrogen gas. The matter density is so low that gravity barely operates. There isn't enough mass to pull things together. Fundamental structure formation stalls. No new galaxy clusters are formed. No rich superclusters emerge. A void forever remains a void. This emptiness creates consequences that seep into physics itself. Gravity is already the weakest fundamental force in nature, requiring colossal masses like planets and stars to show noticeable effects. In a mass-scarce void, gravity becomes even less relevant. The dominant force here becomes dark energy, the mysterious pressure that is accelerating the expansion of the universe. In dense regions filled with galaxies, gravity fights against dark energy, slowing down the expansion in those areas. But inside the voids, gravity loses the tug of war. Dark energy wins overwhelmingly. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward, while the surrounding galaxy filaments act as walls. This creates a self-reinforcing cycle. The more a void expands, the emptier it becomes, which in turn allows for even faster expansion. Scientists have confirmed this through meticulous observations. They measure how galaxies near the edge of the void move compared to galaxies in denser regions. The galaxies in the void are hurrying away from the void center at a rate faster than normal cosmic expansion can explain. Something is pushing them out. That something is the gravity from all the dense matter lying outside the void. Think of the void as a valley surrounded by mountains of matter. Gravity is pulling outward from this valley. This effect is measurable and significant. Our own galaxy is moving away from a local void at a speed of 600,000 miles per hour, about 965,000 kilometers per hour, propelled by this gravitational imbalance. The interior of a void becomes an odd place for physics. Light traveling through it experiences less gravitational influence than light passing through normal space. This subtly affects observations. When astronomers study the cosmic microwave background radiation, the faint leftover light from the Big Bang, they notice that light passing through voids appears slightly cooler. The reduced gravity in the voids causes less gravitational redshift, appearing as cold spots on the temperature map of the early universe. These cold spots line up perfectly with where we observe large voids today. This alignment is no coincidence. It is physics in action. Understanding what makes voids empty helps explain why they are so crucial to cosmology. They are not just boring gaps between interesting galaxy clusters. They are laboratories where dark energy dominates and where gravity must yield. By studying how matter behaves differently in voids versus dense regions, scientists can test fundamental theories about how the universe operates. The KBC void around us may be unsettling because it makes us question the typicality of our cosmic location, but it also provides a rare opportunity. We are perfectly positioned to study the most extreme low-density environments of the cosmos. The structure that contains these voids is far stranger than anyone ever imagined. The universe is not a smooth soup of evenly distributed galaxies. Instead, it resembles a Swiss cheese where dense matter forms walls and filaments surrounding colossal empty pockets. This foam-like structure is called the cosmic web, and it represents the largest architecture in nature. Galaxy clusters condense at the intersection points where multiple filaments meet, creating nodes of extremely high matter density. These nodes shine brightly with millions of galaxies packed relatively close together. Stretching between them are filaments, long strings of galaxy groups that can extend for hundreds of millions of light years. These filaments form walls, vast sheets of matter where galaxies congregate at an above-average density. And nestled between the filaments and walls are the voids. They take up most of the universe's volume, but contain almost no mass. This structure was not always obvious. For decades, astronomers simply took pictures of the sky and counted galaxies. But the true three-dimensional arrangement remained hidden. Distance measurements were poor. Two galaxies that appeared next to each other could actually be billions of light years apart. It wasn't until scientists began systematically measuring the redshift of galaxies in the 1970s and 80s that the cosmic web revealed itself. Redshift surveys allow astronomers to calculate the distance of individual galaxies by measuring how much the expanding space has stretched its light toward the redder wavelengths. Suddenly, the galaxy distribution sprang to life. The universe had structure on scales no one anticipated. The first major void discovery came in 1978. Surveys then continued, each one peering deeper into space and revealing an increasingly complex network. The Sloan Digital Sky Survey, which began in 2000, produced spectacular three-dimensional maps spanning billions of light years. These maps show the cosmic web in stunning detail. Filaments twist and branch like blood vessels. Voids appear as dark bubbles, sometimes up to 500 million light-years wide. The largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light-years long. On the opposite end, supervoids like the Eridanus Void span 1.8 billion light-years, with even fewer galaxies than the KBC Void. Why does the universe organize itself this way? The answer goes back to the beginning. Right after the Big Bang, matter was not perfectly uniform. Quantum fluctuations in the universe's first fraction of a second created tiny density variations. Some regions were slightly denser than the average, and some were slightly less dense. The difference was minuscule, about 1 part in 100,000, but gravity amplifies even the slightest advantage. The denser regions pulled in more matter, making them even denser. The sparser regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, this process became a snowball effect. Small lumps of matter merged into bigger lumps, into galaxy clusters, and then aligned into filaments. Meanwhile, the low-density regions expanded into voids. The cosmic web is essentially gravity doing its work over cosmic time, transforming virtually unnoticeable initial ripples into the greatest architecture in existence. Today, voids occupy about 90% of the volume of space. Filaments and clusters take up the remaining 10%, but contain the vast majority of the mass. This imbalance shapes the character of the universe. We live not in a galaxy-filled universe, but in a universe of emptiness punctuated by infrequent matter concentrations. The KBC Void is just one bubble in this cosmic foam, but it happens to be our bubble, and that makes all the difference to what we observe and how we interpret the cosmos. The next section will reveal exactly where we are sitting inside this vast emptiness. The Milky Way galaxy is not located at the precise center of the KBC Void, but it is close enough to make a difference. Measurements place our galaxy between 200 and 400 million light-years from the Void's center. That is a colossal distance compared to anything a human has ever experienced. But the Void itself extends outward up to 1 billion light-years in every direction from its center, making our eccentricity relatively small. We are nestled well within the Void's low-density region, surrounded by the empty environment in every direction. This location is not accidental. It has consequences for every observation we make and every conclusion we draw about cosmology. If we were located entirely outside the Void, in one of the dense galaxy filaments, our measurements of cosmic expansion would be completely different. We would calculate a slower expansion rate, and the Hubble tension would not exist. Our larger cosmic neighborhood adds a layer to this story. The Milky Way belongs to the local group, which itself is located within the Laniakea supercluster, a gigantic structure containing about 100,000 galaxies. Laniakea is enormous by conventional standards. Yet even this supercluster resides within the KBC Void. Think about that for a moment. A structure containing 100,000 galaxies is still counted as part of the underdensity region. The Void is so vast that it can swallow entire superclusters and still have room to spare. Laniakea forms just one part of the sparse population of matter scattered throughout the Void, one of the rare concentrations in an otherwise desolate region of space. Our position inside the Void also affects what we can see. Light from distant galaxies travels through the Void on its way to our telescopes, experiencing less gravitational interaction. This creates an observational bias. We are not sampling from a random location in the universe. We are sampling from inside one of its most extreme features. Living in the Void means living with a systematic uncertainty about how typical our measurements are. Every measurement you have ever heard about the expansion rate of the universe might be wrong, not because scientists made a mistake, but because we are measuring from inside a cosmic void that is distorting the signal. The problem manifests itself when astronomers use different methods to calculate the Hubble constant, the number that tells us how fast space is expanding. One method looks at the cosmic microwave background, CMB, the ancient light from when the universe was just 380,000 years old. When scientists calculate the expansion rate it should have today, the answer is about 67 kilometers per second per megaparsec. The second method looks at nearby objects, specifically type Ia supernovae, which act as cosmic yardsticks. This local method consistently yields a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. This discrepancy is the Hubble tension, and it has reached 5 sigma statistical significance, meaning there is less than a 1 in a million chance that it is just random variation. The KBC Void explains why these numbers don't match. When we measure the expansion rate using nearby supernovae, we are measuring inside the Void. The Void's low density means there is less gravity pulling back on the expansion. Matter from the denser regions outside tugs on the galaxies inside it, adding an extra outward velocity. Galaxies appear to be rushing away faster than they would in a typical region. This inflates the local Hubble constant measurement. We are not measuring the universe's true expansion rate. We are measuring the expansion rate plus the Void's own peculiar velocity field. This effect is large enough to explain most or all of the observed tension. But here is the uncomfortable point. If the Void explains our local measurements, then those measurements tell us nothing about the universe at large. They tell us about our strange local environment. This means that most headlines you have seen about the accelerating universe and dark energy may be describing a local phenomenon rather than a universal truth. Some scientists object to this conclusion because it violates the cosmological principle, the assumption that Earth does not occupy a special place. This principle states that the universe should look the same from any location. The fact that we find ourselves inside a supervoid that significantly affects our measurements seems to contradict that idea. It suggests that we are in an unusual spot, which makes physicists uncomfortable. Science has gradually removed humanity from special cosmic positions. Earth is not the center of the solar system. The solar system is not the center of the galaxy. And now we are asked to believe that we randomly live inside one of the largest voids ever observed. The statistical improbability bothers many researchers. However, the evidence continues to mount. The void exists. Our measurements don't match, and the void's effects fit the observations. Whether we like the implications or not, the universe may be lying to us about its expansion rate. Or more accurately, our location is causing us to misinterpret what we measure. The crisis this creates in cosmology is deeper than most people realize, and it requires us either to seek new physics or to accept that we are indeed in a special place in the cosmos. In the vast universe, a surprise is unfolding right in our cosmic backyard, a gigantic, empty structure threatening to collapse the foundations of modern cosmic understanding. That is the KBC Void, short for Keen, Barger, and Cowie, a region of space so unimaginably large that matter is extremely sparse, and its existence may hold the key to resolving the Hubble Tension, modern astrophysics' greatest crisis. The Hubble tension is not just a number that is off, it is a signal, a cold whisper from the cosmos suggesting that our understanding of the universe's origin and evolution may be incomplete. When scientists measure the universe's expansion rate, the Hubble constant, they get two irreconcilably different values. One value comes from the early universe via the cosmic microwave background, CMB, and one value comes from the nearby universe, via supernova A. The gap between these two values is the tension, the crisis. The KBC Void theory offers a bold explanation. It is not merely an empty region, it is systematically pushing matter outward. This sounds crazy because gravity, by its very nature, always attracts. But imagine standing in a shallow valley surrounded by towering mountains. Gravity is pulling you toward the mountains, that is, pulling you away from the center of the valley. Inside a cosmic void, galaxies experience a similar effect. All the mass is concentrated outside the void, in the surrounding filaments and galaxy clusters. It is this external matter that exerts the attraction, pulling the galaxies away from the void center toward the denser regions. The result is an outflow, a systematic pattern of galaxies accelerating away from the sparse region. Gravity is not reversed, but the geometry of the matter distribution creates this counterintuitive effect. This outflow is measurable and significant. Astronomers can track the speed of galaxies by combining redshift measurements with distance estimates. When they map velocities around known voids, the pattern becomes clear. Galaxies near the center of the void are moving outward faster than simple cosmic expansion predicts. For the KBC Void, this outflow can add hundreds of kilometers per second to the velocity of the internal galaxies. Even our own galaxy is participating in this pattern. The Milky Way is hurtling away at an incredible speed, 600,000 miles per hour, to escape a nearby local void, driven by this gravitational imbalance. This outflow is the crux of the Hubble tension. When we observe distant galaxies, the redshift we see is a combination of two things: the expansion of space and the galaxy's own peculiar motion due to gravity. Normally, scientists can separate these two components because peculiar motions cancel each other out when looking at a large enough volume. For every galaxy moving toward you due to local gravity, another is moving away. But inside a void, peculiar motions do not cancel out. They all point in one direction, outward. This creates a systematic bias that inflates the apparent expansion rate when measured from inside the void. This complexity changes with distance. Near the void's center, the outflow is rapid. Farther out, the outflow slows down. Beyond the void's edge, the peculiar motion may even reverse as matter falls back toward the dense filaments. When astronomers measure the Hubble constant using supernovae at different distances, they are sampling this complex, changing velocity field. If most supernovae are located inside the void because they deliberately avoid supernovae that are too distant due to other complications, the measurement will be boosted by the outflow. This predicts that the Hubble constant should appear to decrease with distance, and recent observations confirm exactly that trend. Model calculations show that a void with a radius of about 1 billion light-years and a 20% density deficit could easily produce the observed velocity anomalies. The fit between prediction and observation is good enough that many researchers consider the void explanation highly compelling. However, there is a deeper issue. The standard cosmological model struggles to explain how such a large void could form in the first place. Computer simulations rarely generate such extreme voids. The fact that we randomly live in one of these rarest structures right at the time we develop the precision to measure the Hubble constant seems suspicious. This raises a worrying possibility. Perhaps our model of the universe is missing something. If larger and deeper voids than predicted keep showing up, maybe structure formation works differently than the standard theory. Either way, the counterintuitive gravity inside voids is telling us something critical about the evolution of the cosmos. The Milky Way galaxy is not stationary in space. We are hurtling through the universe at a speed that amazes any astrophysicist, about 600,000 miles per hour, equivalent to about 850 times the speed of sound. This colossal velocity does not come from the expansion of space, but from local gravitational effects. More specifically, our galaxy is being pulled away from a nearby local void and toward the denser matter structures lying outside it. The void itself is not pushing us. Rather, the lack of matter inside the void means that the gravitational pull toward it is significantly weaker than the gravitational pull in other directions. The denser regions win the gravitational tug-of-war, accelerating our galaxy out of the sparse region. The speed of 600,000 miles per hour is hard to grasp. It means the Milky Way moves about 167 meters per second. In a year, we travel about 5.2 billion miles through space relative to the void. But even at this tremendous speed, the void is so large that our motion barely makes a dent. It would take hundreds of millions of years to cross from one side of the void to the other. Meanwhile, the void itself is still expanding due to cosmic expansion and dark energy. It is growing faster than we can escape it. We are inside the void now, and we will remain there for the foreseeable cosmic future. Our velocity is a complex composition of many components. Escaping the void, the local sheet, a flattened structure of galaxies including both the Milky Way and Andromeda, is rushing away from the void center at a speed of about 260 kilometers per second. Our galaxy participates in this collective motion, falling toward Virgo. The Milky Way is also falling toward the Virgo cluster, a rich cluster of galaxies about 60 million light-years away. The Virgo cluster contains over 2,000 galaxies and has enough mass to attract everything in the surrounding region, including us. This adds a velocity component of about 250 kilometers per second toward Virgo. Neighboring interaction, the Milky Way and Andromeda are falling toward each other, set to collide in about 4 billion years. That motion also adds another velocity component. When all these gravitational influences are added together, The total peculiar velocity of the Milky Way relative to the cosmic microwave background, CMB, rest frame is about 627 kilometers per second. This is the velocity that astronomers measure when they look at the dipole pattern in the CMB temperature. These motions are crucial because they complicate cosmic measurements. When we observe distant galaxies and measure the redshift, we need to correct for our own motion through space. Otherwise, galaxies in the direction we are moving would appear blue-shifted, and galaxies in the opposite direction would be red-shifted, creating a false pattern. However, inside a void, the corrections become more complex because the void itself creates a large-scale collective flow that spans hundreds of millions of light years. Separating the void effect from the true cosmic expansion requires careful modeling of the local velocity field. Our high speed in space is evidence for the void's existence. If we lived in a typical region with average density, our peculiar velocity would be much smaller, perhaps only 100 or 200 kilometers per second. The fact that we are moving so fast suggests a strong gravitational gradient in our vicinity, exactly what you would expect when near a large underdense region. This velocity perfectly aligns with the void hypothesis and would be very difficult to explain without it. This makes our motion a critical piece of evidence in the debate over whether the KBC void exists and influences our measurements. The universe may be lying to us about its expansion rate, but it cannot hide the fact that we are racing through it at an incredible speed. The existence of the KBC void threatens to break one of the foundational assumptions of modern physics, the cosmological principle. This principle asserts that, on a sufficiently large scale, the universe is homogeneous and isotropic. Homogeneous. The universe looks the same everywhere. No location is special. Isotropic. The universe looks the same in every direction you look. These assumptions have greatly simplified the mathematics of cosmology, allowing scientists to model the entire universe with relatively simple equations. Throughout history, science has gradually removed Earth from any special position. From Copernicus demonstrating that the Earth is not the center of the solar system, to later observations showing that our galaxy is not the center of anything. The cosmological principle is the highest expression of this trend. Every location is equivalent. The KBC void presents a major violation of homogeneity. If this void is 2 billion light-years across with a 20% density deficit, that is a colossal inhomogeneity. Even on cosmic scales, this void occupies a significant portion of the observable universe's volume in our vicinity. What is more concerning is that we happen to live near the center of this anomalous structure, which directly contradicts the idea that our position is unremarkable. Voids are common, but the KBC void is different. Supervoids this large are extremely rare. The fact that we happen to live in one raises the question: is the cosmological principle truly correct, or is it only approximate on much larger scales than previously thought? Scientists calculate that in a universe governed by the standard cosmological model, a void as large and deep as KBC should be extremely rare, perhaps a 10 sigma statistical deviation, a near impossible probability. In a typical random arrangement of cosmic structure, you might not find a single such structure in the entire observable universe. Yet, we are inside one. This suggests that we are extremely lucky, an astonishing random coincidence. The standard cosmological model is wrong about how structure formation works. Defenders of the cosmological principle argue that the void does not violate the principle because homogeneity only applies on scales of a few hundred megaparsecs or larger, and KBC is right on the edge of that scale. Or they suggest that the void's true density deficit is not as extreme as initial measurements suggest, only about 10 to 15% instead of 20%. Another defense is by using the weak anthropic argument. we should not be surprised to find ourselves in an unusual location because observers can only exist in certain types of environments. Perhaps intelligent life requires galaxies to form, and galaxies preferentially form in regions of moderate density, not in the densest clusters or the emptiest voids. If most observers live in slightly under-dense regions, finding ourselves in a mild void is not surprising. However, this argument only works if the KBC void is not too extreme. A 20% deficit is more than mild. It pushes the boundary of what the anthropic principle can explain. The debate over the cosmological principle is far from settled. Some researchers believe the void is real and significant, requiring a revision to cosmology or the acceptance that Earth occupies a truly anomalous position, while others believe it is merely an observational artifact. Future observations, mapping the universe at greater distances and depths, will help resolve this issue. If large voids turn out to be common, the cosmological principle is preserved, but the standard model needs revision. If they are truly rare, we need to explain why we live in one. The origin of the voids we observe today stems from the universe's very first moments, from incredibly tiny quantum ripples. During a phase called inflation, the universe expanded exponentially in a tiny fraction of a second, perhaps 10 to the negative 35th seconds. During this ultra-fast expansion, quantum fluctuations were stretched from subatomic scales up to cosmic scales. These fluctuations created slight variations in the density of matter and energy, only about 1 part in 100,000. But they were enough to set the stage for everything that followed. After inflation ended, matter began to clump together under the influence of gravity. But gravity did not create uniform matter, it only amplified the initial density differences. Regions that were initially slightly denser attracted more matter from their surroundings, making them even denser. This was a positive feedback loop, which created the first stars, galaxies, and galaxy clusters. Conversely, regions that were initially slightly less dense lost matter to the denser regions. As matter drained away, these regions became even emptier and grew into voids. This process, called gravitational instability, transformed those virtually unnoticeable initial ripples into the dramatic large-scale structure we observe today, the cosmic web of filaments, clusters, and voids. The cosmic microwave background, CMB, radiation provides a snapshot of these density variations when the universe was only 380,000 years old. The cooler spots, lower density, on the CMB map are the primordial seeds of today's voids. Scientists can take this model and run it forward in computer simulations, predicting what the structure should look like billions of years later. The fit between prediction and observation is one of the great achievements of modern cosmology. However, as mentioned, these simulations rarely produce voids as large and deep as the KBC void. The initial quantum randomness should produce common small voids, while extremely large voids should be very rare. The existence of KBC raises the question, did the initial quantum randomness have some subtle patterns that enhanced the formation of large voids? Or does gravity operate slightly differently on large scales? When you visualize the universe, you might think of a sky full of stars and galaxies. But the reality is the opposite. The universe is overwhelmingly empty. Voids occupy about 90% of the total volume of space. Galaxies and clusters are crammed into the remaining 10%, concentrated in the filaments and walls surrounding the voids. Even in the void, dark matter still exists, although at a much lower density. And especially dark energy, the mysterious component driving the accelerating expansion of the universe, appears to be uniform throughout space. Because dark energy does not clump like matter, it becomes the dominant component inside voids, where matter is scarce. The interaction between dark matter and dark energy determines the evolution of the voids. As the universe continues to expand and dark energy becomes increasingly dominant, voids begin to accelerate their expansion. This acceleration causes the voids to grow faster over time, eating into the surrounding matter filaments. The future of the universe is inevitable. It will become increasingly empty. Galaxy clusters will become isolated islands in an expanding ocean of emptiness. The quantum accident that happened 14 billion years ago shaped us to live in a slightly underdense region, but the universe's destiny is to become completely empty. Studying the KBC Void, the structure that challenges our fundamental principles, is not just about resolving a numerical crisis. It's about accepting that our position may be anomalous and that our understanding of the universe's origin needs to be deepened. In the grand symphony of the universe, every note obeys a basic rule. The larger and deeper the structure, the rarer it is. Small fluctuations in primordial matter give birth to small voids, only a few tens of millions of light-years across. They are common cracks in the cosmic fabric, but to create larger voids, hundreds of millions of light-years across, requires larger, rarer fluctuations. And then we are confronted with an entity that exceeds all predictions, the KBC Void. This void is staggering in size, spanning over 2 billion light-years and having a matter density about 20% lower than the cosmic average. This is not just a large crack, it is a macro black hole in the cosmic picture. Computer simulations of structure formation using the standard cosmological model, the lambda cold dark matter model, rarely create anything this extreme. When researchers run thousands of simulated universes and search for voids as large and deep as KBC, they find very few matches. The statistical probability of such a void existing is extremely low. Some analyses have attempted to quantify this improbability. One study calculated that the KBC void's size and depth correspond to a 10 sigma deviation from the expected matter density. In statistics, a 5 sigma result already means the chance of it being random is less than 1 in a million. A 10 sigma result is almost unimaginable. You would need to observe trillions of cosmic volumes to hope to find even one such void. Yet the paradox is, we are living right inside one. This is not a small statistical anomaly. It is a massive red flag, a sign that something is wrong, either with our observations or with the accepted cosmological model. If the observations are accurate, which multiple independent studies have confirmed, then our model is fundamentally flawed. There are 3 main possibilities being hotly debated in cosmology. Modify early inflation. The first possibility is that the initial density fluctuations after the Big Bang were not as smooth as standard inflation models predict. Inflation is a theoretical component with little direct evidence yet. If the inflation period created more power on large scales than anticipated, large voids would form more easily. This would force us to revise our understanding of inflation, changing fundamental assumptions about the origin of cosmic structure. Gravity works differently. The second possibility is that structure formation occurred faster or differently than the standard model predicts. If gravity was actually stronger in the past, or if dark matter behaves differently than we assume, structure would form more vigorously, creating larger voids and richer galaxy clusters. Some researchers propose modified gravity theories, where gravity's strength changes with scale or environment. These theories could accelerate structure formation, making colossal voids more feasible. Observational error. The third possibility is that the KBC void is not as extreme as the measurements suggest. Perhaps observational biases or systematic errors in galaxy surveys have made the void appear deeper and larger than it really is. Different research groups using different data sets have produced slightly varying results. Some studies find the 20% density deficit. Others are closer to 10% or 15%. If the true deficit is at the lower end, the statistical rarity would be reduced. However, confirming the void's properties precisely requires more data, especially from upcoming deep galaxy surveys from missions like the Euclid Space Telescope and the Vera Rubin Observatory. The existence of the KBC Void has become a bullet in the debates over the standard cosmological model. Critics of the lambda CDM model point to the void as evidence that the model fails on large scales. They argue that structure formation is still poorly understood and the standard model makes inaccurate predictions. Defenders of the model counter that rare events still occasionally happen and that our accidentally living in a statistical outlier is not impossible, just improbable. They also note that other aspects of cosmology, such as the cosmic microwave background, CMB, fit lambda CDM predictions very well. Abandoning or significantly revising the model based on one anomalous structure seems premature. However, this void cannot be ignored. It is a concrete observation that demands an explanation. Either we accept that we live in a rare, special location which violates the cosmological principle, which assumes Earth is not in a special position in the universe, or we must modify our models to make large voids more common. Neither option is fully satisfactory. Both represent major shifts in how we think about the universe. The KBC Void has become a focal point for cosmological debates precisely because it sits at the intersection of observation and theory, challenging our most fundamental assumptions. Until this tension is resolved, the void remains a cosmic puzzle that cannot neatly fit into our current understanding. These immense cosmic voids, seemingly useless domains, are actually serving an unexpected and critically important scientific purpose. Cosmic voids are the best places in the universe to study dark energy. The reason is simple. Voids are the only regions where dark energy reigns supreme. In dense areas like galaxy clusters, gravity is strong enough to resist the expansion of the universe. These clusters hold themselves together gravitationally despite the space around them expanding. Even on slightly larger scales in the matter filaments, gravity still has an influence, slowing down the expansion of space in those regions. But in voids where matter is sparse, gravity becomes negligible. With no significant pull to counteract it, dark energy completely controls what happens. Voids expand faster than the cosmic average, driven by the outward pressure of dark energy. This turns voids into natural laboratories for measuring the strength and properties of dark energy. Dark energy is one of the most mysterious components of the universe. Discovered in 1998 through observations of distant supernovae, dark energy accounts for about 68% of the universe's total energy. It acts opposite to normal matter and gravity. While gravity pulls things together, dark energy pushes space apart, accelerating the universe's expansion. The precise nature of dark energy is still unknown. It could be the cosmological constant, an unchanging energy density integrated into the very fabric of space. Or it could be a dynamic field whose strength changes over time and space. Distinguishing between these possibilities requires precise measurements of how the expansion accelerates in different environments and at different times in cosmic history. Voids provide a cleaner signal for these measurements than dense regions. In dense areas, gravity complicates things. The local gravitational pull from nearby masses affects galaxy motions, making it difficult to separate the cosmic expansion from local effects. In voids, those complexities are minimal. Galaxies move almost entirely due to cosmic expansion and dark energy. By measuring the expansion rate of voids against predictions, scientists can test whether dark energy acts as a constant or if it varies. If dark energy were stronger in voids than elsewhere, or if it was different in the past, it would show up as deviations from the expected void expansion rate. Another way voids help is through their shape. Dark energy affects not just the rate, but also how the universe expands in different directions. If dark energy is perfectly uniform, voids would expand evenly in all directions, maintaining a spherical shape. But if dark energy had variations, or if there were other unseen forces, voids might expand more in some directions, becoming elongated or distorted. Observations of void shapes can reveal whether dark energy is uniform. Current measurements show that most large voids are approximately spherical, which supports the idea that dark energy is uniform. But the measurements are not yet precise enough to rule out small variations. The expansion history of voids also encodes information about dark energy. Voids have been growing for billions of years, and their current size reflects that entire history. By modeling how a void should grow over time based on different dark energy properties, scientists can compare prediction to observation. For example, if dark energy were weaker in the past and only recently became strong, voids would have grown slowly at first and then accelerated. If dark energy is a constant, voids would grow at a steadily accelerating rate, determined by that constant value. Observations of voids at different distances, corresponding to different times in the past, allow these scenarios to be tested. One particularly useful technique is measuring the void edges. The boundary between a void and the surrounding matter filament is a transition region where the density sharply increases. The sharpness and position of this edge depend on the void's expansion rate, which in turn depends on dark energy. By mapping void edges at different cosmic times and comparing them to simulations, researchers can infer how dark energy has influenced void growth. Initial results suggest that dark energy has been nearly constant over the last few billion years, consistent with the simplest models. The study of dark energy through voids is a dynamic area of research. Future surveys will discover and characterize thousands of voids of various sizes and distances. Each void provides an independent measurement of dark energy's influence. If voids reveal that dark energy is changing or has structure, it will revolutionize cosmology. Even confirming that dark energy is constant and uniform will be highly significant, as it will rule out many alternative theories. Either way, voids are proving to be essential tools for probing one of the universe's deepest mysteries. And the KBC Void, as the largest and nearest supervoid, offers the best opportunity for detailed study, allowing measurements impossible for distant voids. The galaxies that form inside these cosmic deserts face unique challenges. Galaxies inside cosmic voids grow up in deep isolation. Unlike galaxies in dense clusters, which constantly interact with neighbors, void galaxies evolve in isolation. This difference in environment shapes everything about them. Void galaxies tend to be smaller and fainter than galaxies in filaments. They have lower mass, fewer stars, and less overall matter. Many void galaxies are classified as dwarf galaxies, barely massive enough to hold on to their gas against external pressure from star formation. Their isolation means they rarely undergo galaxy mergers, which are common in dense regions. Mergers are major drivers of galaxy evolution, triggering star formation bursts and feeding central black holes. Without mergers, void galaxies evolve more slowly and remain less developed. The star formation rate in void galaxies is generally lower, but there is a paradoxical surprise. Although most form stars slowly, a higher proportion of them are starburst galaxies, undergoing short, intense periods of rapid star formation. This might seem contradictory until we consider their gas content. Void galaxies are often unusually gas-rich, containing large amounts of neutral hydrogen that have not been converted into stars. In dense environments, interactions with neighboring galaxies can strip away this gas. In the void, galaxies retain their gas longer. When star formation does ignite, perhaps triggered by internal processes rather than external interaction, the abundant fuel supply kicks in. The result is a violent starburst, rapidly consuming the gas before returning to a quiet state. The morphology of void galaxies is also distinct. Most are late-type spiral or irregular galaxies rather than elliptical galaxies. Elliptical galaxies primarily form through mergers, which are rare in the void. Without mergers, galaxies maintain their disk structure and spiral arms. Some void galaxies show an amazingly undisturbed morphology, with smooth disk profiles and regular rotation patterns. They are not battered by interactions or tidal forces from neighboring objects. This makes them excellent laboratories for studying how galaxies evolve in peaceful environments. The dark matter halos around void galaxies are another interesting feature. Dark matter dominates the mass of every galaxy, forming a halo that extends far beyond the visible stars. In the void, these halos are less subjected to external gravitational influence. They retain a more spherical and undisturbed shape compared to halos in clusters, which are often stretched and distorted by tidal forces. The simpler halo structure in the void makes them easier to model and study. The colossal structure containing all these scattered void galaxies is even stranger. The Laniakea supercluster is an incredible structure identified in 2014 that redefines our local cosmic region. Laniakea contains about 100,000 galaxies spanning 520 million light-years. The name originates from Hawaiian, meaning immeasurable heaven. Our Milky Way galaxy is located in the outskirts of Laniakea, part of a vast cosmic drainage basin where galaxies flow toward a central gravitational region called the Great Attractor. Here is the paradox. Laniakea, despite containing 100,000 galaxies, is located entirely within the KBC Void. How can a supercluster, one of the largest bound structures in the universe, exist inside an underdensity region? The answer lies in how density is defined. The KBC Void is underdense compared to the cosmic average when measured on very large scales, billions of light-years. But it is not uniformly empty. It contains local concentrations of matter, like Laniakea, which are denser than their immediate surroundings. These are the remnants of structure formation, islands of matter that resisted depletion as the void formed. From a large-scale perspective, the region is sparse. But when you zoom into the scale of a few hundred million light-years, you find significant structure. Laniakea occupies a portion of that volume. It is large compared to typical superclusters, but small compared to the void itself. Gravitational flows inside Laniakea provide the best evidence for how gravity organizes matter. By mapping the velocities of galaxies in and around the supercluster, astronomers constructed a three-dimensional flow map. The closer galaxies are to the Great Attractor, the faster they fall toward it. The Milky Way's peculiar motion points toward the Great Attractor, confirming that we are gravitationally bound to Laniakea. But Laniakea itself is falling toward something even bigger. The Shapley supercluster, located about 650 million light-years away, is the most massive structure in our vicinity, exerting a powerful pull. The KBC Void alters these flows by adding an outward component. Galaxies simultaneously fall toward local gravitational attractors like the Great Attractor and flow outward, away from the void center. The combination creates complex velocity patterns. We are not at the center of the void in complete isolation. We are offset from the center, located in a region of moderate density, but still underdense compared to the cosmic average. The paradox is resolved when you realize that large-scale and small-scale structures coexist. The void describes the average properties over billions of light-years. Laniakea describes the local properties over hundreds of millions of light-years. Both are real, and both are important for different aspects of cosmology. The measurements that reveal all this rely on a cosmic ruler built from sound waves in the early universe. Baryon acoustic oscillations, BAO, are frozen sound waves from the early universe, and they have become the most reliable yardstick for measuring cosmic distances. In the first 380,000 years after the Big Bang, the universe was a hot plasma where matter and radiation were tightly coupled. Sound waves propagated through this plasma, creating density fluctuations. When the universe cooled enough for atoms to form, the sound waves were frozen in place. The distance these waves traveled before freezing left an imprint on how matter is distributed today. That distance is about 490 million light-years, and it appears as a characteristic scale in the clustering of galaxies. Astronomers can measure this scale and use it as a standard ruler because the physics that created it is well understood. This ruler works at all distances. By comparing the apparent size of this ruler at different distances, scientists can map how the universe has expanded over time. It's like placing identical meter sticks at various distances and measuring how large they appear. If the universe's expansion is accelerating, the distant meter sticks look smaller than expected. This technique is called BAO analysis, and it has revolutionized distance measurements in cosmology. Using this technique, researchers have mapped the three-dimensional distribution of galaxies over billions of light-years. These maps reveal the cosmic web with unprecedented detail. And they also revealed the KBC Void. When scientists analyze the galaxy distribution in our local region and compare it to predictions from BAO, they find a clear deficit. The void appears as a region where the observed scale of galaxy clustering deviates from what distant measurements predict. This mismatch is precisely what you would expect if you are located inside an under-density region. BAO measurements provide independent confirmation that the void exists and quantify its depth and extent. Major projects like the Sloan Digital Sky Survey, SDSS, and the Baryon Oscillation Spectroscopic Survey, BOSS, spent years gathering this data. Processing it requires sophisticated statistical analysis to extract the BAO signal from the noise. BAO measurements have traced the expansion history of the universe. These measurements have revealed something surprising. The expansion history seems slightly off from the predictions based on the cosmic microwave background. The most pronounced deviations are at low redshift, meaning the recent cosmic history, and they are consistent with our location inside the KBC Void. Galaxies inside the void show a slightly higher redshift than expected for their distance when using the BAO ruler. This is consistent with the outflow velocity, adding to the cosmic expansion signal. Therefore, BAO measurements provide yet another line of evidence for the void and its impact on our observations. They show that the Hubble tension, the difference between local and global cosmic expansion rate measurements, is not confined to supernova measurements, but appears across multiple independent techniques. Even the temperature of the universe reveals the void's fingerprint. The cosmic microwave background, CMB, fills the entire universe with faint leftover light from the Big Bang. Its temperature is astonishingly uniform, about 2.7 Kelvin. But that uniformity is not perfect. Tiny temperature variations exist, often only a few parts per million. Light from the CMB has traveled through 13.8 billion years of cosmic evolution to reach us. Throughout that journey, it passes through structures that formed along the way, including voids. When light enters a void, it experiences less gravitational influence than light passing through dense regions. This creates a measurable effect called the Integrated Sachs-Wolf effect, ISW. When a photon falls into a slightly underdense region, it gains a tiny bit of energy from the gravitational potential. When it climbs out, it loses energy. Normally, these effects would perfectly cancel out, but if the void is expanding while the photon passes through, which happens due to dark energy, the cancellation is no longer perfect. The photon ends up with slightly less energy than it started with, which manifests as a tiny temperature drop. This effect is minute, but can be detected when you average over many voids. Scientists have searched for this effect in the CMB map, and they have found evidence of cold spots corresponding to large voids. Although difficult to separate from primordial CMB variations, there is a strong correlation between the largest void in our vicinity and a cold spot on the CMB map. This CMB fingerprint is a third entirely independent piece of evidence for the existence and influence of the KBC Void. Until this tension is resolved, either by accepting our rare location or by modifying fundamental laws of physics, the KBC Void remains a critical cosmic mystery, challenging the architecture of the standard cosmological model. We are a tiny dot suspended in the indescribable vastness of the universe. For decades, standard cosmological models have painted a picture of a homogeneous universe where matter is distributed almost evenly across large scales. But what if that picture is wrong? What if we are not an arbitrary dot in a uniform picture, but the center of something unusual? Astronomers, through deep galaxy surveys, have located large, nearly empty regions in the nearby universe. They are called cosmic voids, gigantic bubbles of space where the density of matter is much sparser than the cosmic average. Among them, a particular structure surrounds us, an underdensity region stretching out in every direction, the KBC Void, Keenan-Barger-Cowie Void. To probe the existence of these voids, scientists have turned their attention to the most ancient light we can observe, the cosmic microwave background, CMB. The CMB is the faint residual light from the Big Bang, a cooled, glowing curtain that covers the entire sky. Its average temperature is a cosmic constant, but as this light passes through gigantic structures like the KBC Void, it carries a subtle physical imprint, a temperature smudge. Astronomers have looked at the CMB temperature in directions that coincide with the locations of identified large voids, and they found a striking correlation. The average temperature in those directions is about 10 millionths of a degree colder than the cosmic average. This number is extremely small, but statistically it is significant. It matches precisely the predictions from physical theory. This correlation confirms that voids actually influence the CMB through a phenomenon called the integrated Sachs-Wolf ISW effect. Imagine a CMB photon traveling through a colossal void. Normally, when a photon enters a high matter density region, a gravitational potential well, it gains energy and appears slightly hotter. Then, when it leaves, it loses that energy back, and the two effects cancel out. However, in a universe dominated by dark energy that is accelerating the expansion, this is no longer true. As the photon passes through a void, the cosmic expansion causes the potential well to shallow or deepen during the photon's passage. Specifically, in a void and underdense region, the faster expansion causes the gravitational potential to weaken while the photon is passing through. As a result, the photon loses a small amount of energy. That lost energy is measured as a drop in temperature, the cold smudge we observe. For the KBC Void, this effect should be particularly strong because of its size. The CMB light passes through almost the entire void, accumulating that temperature deficit over its billion light-year length. This leads us to one of the most enigmatic features in the CMB map, the cold spot discovered by the Wilkinson Microwave Anisotropy Probe, WMAP. This region is about 5 degrees across the sky and is about 100 millionths of a degree colder than surrounding areas. It is abnormally large and cold compared to the random fluctuations predicted from the early universe. One proposed explanation is that this cold spot is the result of a supervoid located along that line of sight. If a particularly large and deep void blocks the way, it could generate the observed temperature deficit via the ISW effect. However, this connection remains controversial because the supervoid needed to explain the cold spot would be statistically extremely improbable in standard cosmology. The KBC Void is not aligned with that cold spot. Instead, it surrounds us in every direction, like a cosmic wrapping. Therefore, its temperature signature is more subtle, showing up as a modification to the overall CMB pattern rather than a localized anomaly. To detect this signature, careful modeling of the CMB shape with and without the presence of the KBC Void is required. Preliminary analyses suggest that the void's presence is consistent with the observed CMB, providing an independent verification of its existence and properties. The CMB temperature measurements also place limits on the void's properties. If the KBC Void were much deeper or larger than current estimates, it would produce a stronger temperature signal that should have been seen. The absence of any significant anomaly appearing in our direction suggests that the void has a density deficit of around 20% and extends for about 1 billion light-years, consistent with other independent measurements. This consistency is comforting. It suggests that multiple independent lines of evidence all point to the same basic picture. We live in a large under-density region, but its properties are not excessively extreme. However, its very existence opens up a deeper question. The KBC Void, a colossal anomaly surrounding us, is challenging our most fundamental understandings of the universe. Is it merely a strange coincidence, or a call to rewrite a century-old physics textbook? The answer lies in gravity itself. The existence of the KBC Void forces us to confront a difficult question. Why does such a gigantic and empty structure exist in our neighborhood? In light of the lambda CDM, lambda cold dark matter model, the standard cosmological model that uses Einstein's general relativity, the KBC Void is an extremely improbable statistical event. Computer simulations based on lambda CDM show that such large structures could only have formed from very rare primordial density fluctuations. The fact that we happen to live right near the center of such a cosmic rarity makes many scientists uncomfortable. Are we in an unreasonably lucky special position, or is our theory of gravity incomplete on the largest scales? The foundation of modern cosmology is Albert Einstein's general relativity, GR, formulated in 1915. For over a century, this theory has passed every test, from predicting the bending of light around massive objects to explaining the orbital decay of binary pulsars. General relativity has been the physicist's guide. However, the KBC Void is challenging this foundation in unexpected ways. If the void is too large and too deep to form naturally in simulations based on GR and lambda CDM, then perhaps gravity doesn't operate exactly as Einstein predicted on colossal cosmic scales. Some scientists propose modifying gravity rather than accepting that we live in a position of low statistical probability. MUND, modified Newtonian dynamics, is the most prominent alternative gravity theory proposed by physicist Mordechai Milgram in 1983. MUND theory proposes that gravity behaves differently when acceleration is extremely small, below a certain threshold. At high acceleration, like on Earth or in the inner solar system, gravity follows Newton's and Einstein's laws perfectly. But at the tiny accelerations involved at the edges of galaxies and on cosmic scales, gravity becomes stronger than general relativity predicts. This modification was originally proposed to explain galaxy rotation curves without invoking dark matter. galaxies rotate faster than visible matter alone can account for. MOND solves this by boosting gravity at large distances. Although MOND has struggled to explain many cosmological observations, like the CMB, it does a better-than-expected job of explaining some features of the cosmic web. In MOND cosmology, structures form more efficiently because gravity is enhanced on large scales, pulling matter together more strongly. This creates richer superclusters and deeper voids than standard gravity. Computer simulations using MOND gravity create large voids like KBC naturally without needing improbable initial conditions. The statistical improbability vanishes. The void becomes an expected consequence of how structure forms under modified gravity. This is a compelling feature because it resolves the tension between observation and theory without resorting to extreme luck. However, MOND faces serious challenges. CMB MOND has difficulty explaining the temperature fluctuations of the CMB, which standard cosmology explains beautifully with general relativity. Gravitational lensing. MOND does not easily explain observations of gravitational lensing, the way massive galaxy clusters bend light. The observed amount of lensing requires more gravity than visible matter, plus MOND's modification can provide, suggesting that dark matter is still needed. Some researchers have developed hybrid models that combine MOND with a small amount of dark matter, often in the form of neutrinos. These models might be able to explain both the CMB and the enhanced structure formation seen in the cosmic web. Another class of modified gravity theories involves changing how gravity propagates over large distances rather than changing its strength. These theories introduce extra fields or higher dimensional effects that alter the gravitational dynamics on cosmic scales. Some of these theories predict that gravity becomes effectively stronger in low-density regions like voids, which would make large voids easier to form. Testing these theories requires precise measurements of how matter moves in voids compared to dense regions. If the velocity patterns deviate from general relativity's predictions, it could be a sign of modified gravity at work. The debate between modified gravity and standard cosmology with a chance void is unresolved. The KBC Void has become a battleground where fundamental physics is being tested. If the KBC Void is not just a density anomaly, but a sign that our cosmic measurements are distorted, then one of the most crucial numbers in cosmology, the age of the universe, is at stake. Current measurements based on the cosmic microwave background, CMB, place the universe's age at 13.8 billion years. This number comes from detailed models of how the universe expanded from the Big Bang to the present, using the cosmic expansion rate and other parameters like the density of matter and dark energy. This result is considered highly reliable. The problem arises from the Hubble tension. The locally measured expansion rate is significantly faster than the rate inferred from the CMB. If the local expansion rate, i.e., the rate measured within the KBC Void's range, truly represented the global expansion rate of the universe, then the universe has been expanding faster throughout its history. A faster expansion rate means the universe reached its current size in less time. Calculations suggest this would make the universe about 8% younger, placing its age at around 12.7 billion years instead of 13.8 billion years. This is not a minor discrepancy. It creates a major conflict with other observations. The oldest stars in globular clusters, dense ancient star populations, appear to be around 13 billion years old, based on stellar evolution theory. You cannot have stars older than the universe itself. Their age is determined by observing which mass of stars has reached the end of its life, the turn-off point. The oldest globular clusters show that the most massive remaining stars have only just survived, suggesting the clusters formed about 13 billion years ago. If the universe is only 12.7 billion years old, then either our stellar age measurements are systematically wrong, or our cosmic model is wrong. If stellar ages are correct, the universe cannot be as young as the local expansion rate suggests. White dwarfs provide an independent age measurement. White dwarfs are the remnants of dead stars, which cool down gradually over billions of years. The coldest white dwarfs we observe have been cooling for around 12 to 13 billion years, again suggesting the universe must be at least that old. This measurement does not depend on the main stellar evolution models, making it harder to adjust. The age tension, like the Hubble tension, can be resolved if the local expansion rate does not represent the global average. If the KBC void is inflating our local measurements, then the CMB estimate of 13.8 billion years is likely correct. The universe would be old enough for the observed stars and white dwarfs to exist. The age tension highlights a deeper issue: the influence of the local environment on observations. Argument 1, stellar age depends on local physics, such as nuclear reaction rates, and is unaffected by whether we live in a void or not. How long a star burns hydrogen is unrelated to cosmic expansion. Argument 2, initial conditions for star formation depend on cosmic history. If the KBC void affected structure formation, the first stars might have formed earlier or later than in typical regions. However, the internal consistency, that objects inside the void, stars in our Milky Way, have ages consistent with the age of the universe inferred from the distant CMB, suggests that the void explanation, while compelling, may not be the entire story. The age conflict forces us to choose between a successful cosmic model, a tested theory of stellar evolution, and a questionable local measurement of cosmic expansion. The KBC void offers a way out, but another layer of complexity remains concerning how galaxies move. As cosmologists debate the age of the universe and the nature of gravity, another piece of physical evidence has emerged from the actual movement of matter. Galaxies are not stationary. They move through space in response to the gravitational pull from surrounding structures. These movements are called peculiar velocities, distinct from the overall cosmic expansion. In standard cosmology, these peculiar velocities should be relatively small and random on large scales. When averaged over volumes hundreds of millions of light years across, this movement, called bulk flow, must be close to zero. This is what the homogeneity principle predicts. If the universe is uniform, there will be no large-scale gravitational gradients to drive these flows. Observations, however, tell a different story. Measurements of galaxy velocities show significant bulk flows extending out to distances of 200 to 300 million light-years. These flows reach velocities of 400 kilometers per second, or more, much higher than standard cosmology predicts. Crucially, on these large scales, the flows are coherent. Galaxies across massive volumes are all moving in nearly the same direction. This suggests the presence of a large-scale structure that is creating a gravitational gradient to pull matter in specific directions. The KBC void is precisely the type of structure that could generate these flows. Matter inside the void is accelerating outward toward the denser regions at the void's edge. This creates a bulk flow directed away from the center of the void. Models simulating how galaxies would move if they were located inside a large underdensity region surrounded by dense shells of matter show that the predicted velocities and flow patterns closely match the observations. The flow is strongest near the void edges, where the density gradient is sharpest. A 20% density deficit spanning a billion light-years generates flows of about 400 kilometers per second, exactly what is observed. This striking agreement provides strong support for the void hypothesis. Standard cosmology without the KBC Void struggles to explain these flows. Lambda CDM simulations predict bulk flow should drop off quickly, falling below 100 kilometers per second at the 200 million light-year scale. Once again, observations point to more structure on large scales than standard models comfortably predict. This further fuels the argument that lambda CDM is missing something, perhaps in dark matter, dark energy, or gravitational physics itself. The KBC Void is not the largest known underdensity region. That title belongs to the Eridanus supervoid, discovered via its impact on the CMB. Located in the constellation Eridanus, this void is about 1.8 billion light-years across, a scale comparable to KBC. What makes it especially intriguing is how it was found. Astronomers weren't counting galaxies, they detected it by noticing an anomalous cold spot in the CMB temperature map, the cold spot we discussed. This cold spot corresponds to a region where the microwave radiation is about 70 millionths of a degree colder than the average. It is so unusually large and cold that it occurs in only about 2% of simulated universes. When astronomers surveyed the galaxy distribution in the direction of the cold spot, they found evidence of a large underdensity region aligned with it. This Eridanus void is located about 3 billion light-years from us. Light from the CMB travels through this void, undergoes the integrated Sachs-Wolf effect, loses energy, and shows up as a temperature deficit. Calculations suggest a void of Eridanus's size and depth can explain about half of the observed cold spot temperature anomaly. The story of the KBC Void and the Eridanus supervoid highlights a running theme. Our local cosmic environment is more dynamic and structured than simple homogeneous models assume. Does this mean that we live in an unusual location? Our cosmological models need revision, the solution favored by modified gravity proponents. Future observations, particularly more precise bulk flow measurements at greater distances, will help settle this debate. If the flows remain robust, it will continue to challenge standard cosmology. Either way, the KBC Void is not just a hole in space, it is a battleground where fundamental physics is being tested. Our telescopes have painted a picture of the universe, a vast and complex cosmic web where luminous filaments of galaxies glitter like threads of light, embracing nearly empty regions of space, the cosmic voids. But there are voids, supervoids, that challenge our every notion of emptiness. We're talking about colossal dark regions where the density of matter is significantly lower than the cosmic average. Imagine this. Half of this emptiness could be due to random chance, a coincidence with a cold fluctuation in the primordial cosmic microwave background. Or it could be a sign that this void is larger and deeper than our current measurements can capture. The Eridanus supervoid, like the KBC Void, poses the same fundamental question. How can such a vast underdense region form? Does its existence fit the standard cosmic model, or does it require unusual starting conditions? The fact that this void was predicted by the cosmic microwave background cold spot before being confirmed by galaxy surveys has bolstered belief in its existence. However, measuring its precise properties remains a major challenge. At that distant range, galaxy surveys become less complete. Many faint galaxies are missed, making it difficult to accurately quantify the density deficit. Current estimates place the deficit at around 20 to 30% below the cosmic average. If both the KBC Void and the Eridanus supervoid are real and as extreme as measurements suggest, it raises the possibility that such voids are more common than the standard cosmic model predicts. Two large supervoids in the observable universe might still be consistent with the lambda cold dark matter model if we accept some statistical deviation. But finding 3 or 4 would become increasingly difficult to explain. Future, deeper surveys will continue to map the universe to even greater distances, uncovering more voids. The statistical distribution of void sizes and depths will be a critical test of whether structure formation matches predictions. If large voids are common, it suggests that either we misunderstand structure formation or we are living in an atypical part of the universe where large voids happen to cluster. Both options are uncomfortable for cosmologists. The Eridanus supervoid also demonstrates that voids influence observations in measurable ways. The temperature deficit they create in the cosmic microwave background is small but detectable. The velocity fields they create are also observable through bulk flow measurements. These effects are not just theoretical predictions. They are real phenomena that astronomers can study. This offers hope that the mysteries surrounding the KBC Void and the Hubble Tension may eventually be resolved through better observations. If voids systematically bias measurements, those effects can be corrected for or modeled. The challenge is gathering enough data to accurately characterize the void structure of the universe. One thing is clear: the universe contains more large voids than initial cosmological models expected. Whether this reflects the rarity of our cosmic region or a flaw in our models remains an open question. Our measurements are only truly reliable when we look far away, beyond our immediate neighborhood. The term Hubble bubble has emerged to describe a worrying observational pattern. When astronomers measure the Hubble constant, which represents the universe's expansion rate, using nearby objects such as supernovae within about 2 billion light-years, they obtain higher values, around 73 kilometers per second per megaparsec. But when they use objects farther than 2 billion light-years or rely on data from the cosmic microwave background, CMB, they obtain lower values, around 67 kilometers per second per megaparsec. This approximate 2 billion light-year boundary is suspicious as it lies near the exact edge of the KBC Void. Image illustrating the Hubble bubble hypothesis, where the expansion rate is higher inside the local void. This has led to the hypothesis that measurements inside the void are being affected by its presence, creating a bubble of biased observations. Only by looking outside the bubble can we see the universe's true expansion rate. This hypothesis makes a clear prediction. The measured Hubble constant should change with distance. Nearby measurements should show the highest value. As you look farther out, approaching and crossing the void's edge, the measured value should gradually decrease toward the cosmic average. Beyond 2 billion light-years, it should stabilize at the lower value. And this is exactly what recent observations are starting to show. Studies using supernovae at various distances are finding that the inferred Hubble constant gradually declines with redshift. This trend is not yet conclusive, as measuring distances to very far supernovae is challenging and the uncertainties are large. But the direction of the trend matches the prediction from the Hubble bubble hypothesis. If this bubble is real, it creates a significant issue for cosmology. Most of our local expansion rate measurements must use nearby objects, as they are the only ones we can observe in enough detail. More distant objects are fainter and harder to pinpoint accurately. This means that our most reliable local measurements are precisely the ones most affected by the void. We are stuck inside the bubble, unable to step outside our local environment to see what the universe truly looks like. It's like trying to determine Earth's climate by only measuring the temperature inside a heated building. You can take very precise measurements, but they are not representative of the global average. To break the bubble, it is necessary to observe objects farther than 2 billion light-years with an accuracy comparable to nearby objects. This is technologically difficult, but becoming feasible. Space telescopes like the James Webb Space Telescope can observe distant supernovae in unprecedented detail. These distant probes offer a window into the universe outside the bubble. Initial results suggest that the distant universe expands at the rate predicted by the CMB, which is consistent with the bubble hypothesis. But the data is still limited. More observations are needed to confirm the trend and establish whether it fully resolves the Hubble tension. The bubble concept also applies to other measurements. Bulk flow observations show significant motions out to about 300 million light-years, but they seem to decline at larger distances. This is consistent with the void creating a local velocity field that dissipates as you approach the void's edge. Baryon acoustic oscillation measurements also show discrepancies mainly at low redshift, again suggesting local effects. Multiple independent lines of evidence point to one conclusion. Our local environment, within about 2 billion light-years, is systematically different from the universe at large. We are living in an island of anomalous properties, surrounded by a more typical cosmos. Accepting the Hubble bubble hypothesis requires accepting that many of the measurements we use to understand the universe are biased by our location. Philosophically, this is uncomfortable. Scientists prefer to believe that their observations represent universal truth, not local accidents. But the evidence increasingly suggests that we cannot escape local bias without looking far enough away, where the void's influence fades. If the bubble is real and it explains the Hubble tension, then cosmology can breathe a sigh of relief. The standard model still works. We just happen to be measuring from a strange location. But if the tension persists, even at large distances, then new physics will be required. Cosmic voids do more than just skew measurements. They affect the very ability of structure to form inside them. Cosmic voids act as filters, preventing certain types of structures from forming within their boundaries. In the dense regions of the cosmic web, galaxies frequently collide and merge. Small galaxies combine into larger ones. Gas is stripped from galaxies due to interactions with the hot intracluster gas. Supermassive black holes at the centers of large galaxies grow by accreting matter. This process drives rapid evolution, transforming small, irregular galaxies into large, old, red elliptical galaxies over billions of years. But in voids, this evolutionary track is stalled. The low density means gravity is weak. Small structures like galaxies can still form, but larger structures, such as giant galaxy clusters or large galaxy groups, require more gravity than the void can provide. The matter density is simply insufficient to pull such large concentrations of mass together. As a result, voids remain perpetually underdeveloped. The largest structures that form inside them are only modest galaxy groups. This creates a limit on structure growth. Voids are stuck in a state of evolution that dense regions passed through billions of years ago. This filtering effect has profound implications for galaxy evolution. In dense environments, frequent mergers consume galaxies' gas and shut down star formation. Galaxies become red and dead, filled with old stars but forming very few new ones. Image illustrating the difference in galaxy morphology and color between void galaxies, blue spiral, and cluster galaxies, red elliptical. But in the void, mergers are rare. Galaxies retain their gas and continue to form stars slowly over billions of years. They remain blue and star-forming for much longer than their cluster counterparts. This explains why void galaxies tend to be late-type spirals with continuous star formation, rather than early-type elliptical galaxies dominated by old stars. The filter also affects the intergalactic medium, the diffuse gas between galaxies. In dense regions, this gas is heated to millions of degrees by shock waves from collisions and energy from supermassive black holes. In the void, the intergalactic medium remains cooler and denser, closer to the conditions in the early universe. This makes voids excellent laboratories for studying primordial gas and how it is gradually incorporated into galaxies. This filtering effect is self-reinforcing because large structures cannot form in the void. The void environment remains unchanged. There are no rich galaxy clusters to pump energy into the intergalactic medium. Meanwhile, dense regions continue to evolve, becoming richer and more complex. This creates an ever-increasing contrast between voids and filaments. The structure of the universe becomes more extreme over time, with voids becoming emptier and filaments becoming denser. Dark energy accelerates this trend by boosting the void's expansion. The grand filter concept has implications for life in the universe. If advanced civilizations require certain environmental conditions, such as stable galaxies with continuous star formation, then voids might be more hospitable than dense regions. Void galaxies experience fewer catastrophic events, such as nearby supernovae or gamma-ray bursts that could sterilize planets. Isolation provides long-term stability. On the other hand, the low star formation rate in the void means there are fewer heavy elements for planet formation. Void galaxies tend to be metal poor, which may limit the types of planets that can form. Whether voids enhance or diminish the prospects for life remains an open question. But if we are living in a void, it could influence the galaxy we are in and the conditions that allowed Earth to flourish. Are we typical void inhabitants, or are we an anomaly? The answer lies in the contrast between our isolated region and the vast universe outside. The future of voids is a future of increasing isolation. Dark energy is driving the accelerating expansion of the universe, and that acceleration carries serious implications for the distant future. As space expands faster over time, structures not bound by gravity will drift apart and eventually lose all contact. This process is already underway, but it will intensify in the billions and trillions of years to come. Voids will expand faster than the universe as a whole because they contain less matter to resist the expansion. The filaments surrounding the voids will thin out as the galaxies within them are stretched farther apart. Eventually, even neighboring superclusters will lose causal contact as the space between them expands faster than the speed of light can cross. The universe's fate is ever-increasing isolation, with structures becoming islands separated by relentlessly expanding voids. For galaxies deep within a void, this isolation will be profound. Currently, galaxies in the KBC Void can still see surrounding filaments and clusters at great distances. But as dark energy drives accelerating expansion, light from increasingly distant objects will never reach us. The cosmic horizon, the boundary that light cannot cross before the universe expands too much, will shrink over time. Image illustrating the shrinking cosmic horizon and increasing isolation of galaxy clusters. Objects currently visible will fade from sight as their light is redshifted into invisibility. Galaxies deep within the void will find themselves in an increasingly empty sky with fewer visible neighbors. The cosmic microwave background will become cooler and fainter until it is undetectable. This poses a troubling question for future civilizations. If a civilization were to arise in a void galaxy billions of years from now, what would they be able to learn about the universe? Their sky would be nearly empty, save for their local galaxy group. There would be no evidence of the Big Bang, no distant galaxies to measure cosmic expansion. They would be cosmically isolated, unable to observe the larger universe because light from outside their immediate neighborhood could not reach them. Such civilizations might conclude that they live in a static island universe surrounded by empty space, never suspecting the vast cosmos beyond their horizon. This scenario, sometimes called the dark future, is the inevitable consequence of accelerating expansion. Even in our own void, the long-term future looks lonely. The Milky Way and Andromeda will merge to form a giant elliptical galaxy, but this local group itself will become increasingly isolated. Other nearby groups will recede beyond our cosmic horizon in the tens of billions of years. Star formation will gradually cease. The galaxy will dim, leaving behind only red dwarf stars, and eventually white dwarfs, neutron stars, and black holes. The night sky will darken. On even longer timescales, trillions of years from now, stars will become rare. Galaxies will consist mostly of dead stellar remnants, slowly evaporating into space through gravitational interactions. Ultimately, even black holes will evaporate via Hawking radiation, a quantum process that causes them to lose mass over unimaginably long timescales. The final state of the universe will be a sea of diffuse particles and radiation, eternally expanding in darkness. The voids will consume everything, with the last remnants of structure dissolving into the infinite expanse of the void itself. The cosmic web we observe today, with its intricate filaments and clusters, is just a temporary stage. The true long-term structure of the universe is emptiness, interrupted by isolated, increasingly separated islands of matter. We are living in an unusual time when the universe still has rich structure. Billions of years from now, the void will be everything. A final question remains about our position in this cosmic void. Can we accurately understand the universe, or are we permanently limited by our anomalous vantage point? We think we understand the universe quite well based on observations from inside the KBC Void. But what if there are systematic biases we haven't accounted for? What if the universe outside the void looks fundamentally different from what we observe locally? Future observations extending far beyond the void will test this. If distant regions confirm our local conclusions, we can be confident that our understanding is correct. If they reveal systematic differences, we may need to revise our entire cosmological framework. We are inside a 2 billion light-year cosmic hole. This is not metaphor or speculation, it is observation. The KBC Void is real, its influence is measurable, and its existence challenges fundamental assumptions in cosmology. The universe is far stranger than we imagined, and our place in it is more unusual than we ever suspected. We are cosmic castaways, drifting through a desert of space, measuring a universe that may not be what it seems.